Center is Daniele Chiappini. Sorry, I don't know your name, So first speaker is Daniele Chiappini from University of Rome Niccolò Cusano, and he's going to present the overview on a couple kinetic-free surface approach for fluid structure interaction problems. So whenever you are ready, the floor is yours.
Perfect. Thank you, Giovanni, for your introduction. Hope you may see my full screen presentation. The work I'm presenting you has been made together with my colleague Silvia Di Francesco, and it was a part of an Italian Ministry of Education funded program about fluid structure interaction problems. The outline of my presentation will be the following. First of all, some motivation. After that, a short update about the model we are using. So the KBC model in the LBM panorama, the free surface model we have coupled with the KBC1, and finally, how do we deal with the fluid structure interaction in the case of rigid obstacles. After that, I will present you our model validation with some test cases already presented in literature, and finally the results and some preliminary result on sloshing. Okay, motivations. Why are we interested in multi-phase and fluid structure interaction application? Basically, because they are ubiquitous. They are, whatever you look at, you may face up with the fluid structure interaction. And if we focus on naval engineering, the impact of a boat on the sea may be obviously seen how in the range of a fluid structure interaction, or for example, a tank which is moving water can be seen as a fluid structure interaction problem. So the mutual influences in between moving a fluid into a solid container is really of a paramount importance in many applications. In literature, there are plenty of studies which have highlighted and deeply studied the impact of rigid obstacles on water. But we may also think to small organisms which are swimming or the interaction of blades with the air. So you see that the fluid structure interaction is really a huge panorama where we can look at. In this huge ballpark, we are focusing on the analysis of the impact of obstacles on water. So basically, if you look at a falling object which is impacting the water, actually we are talking about a ternary system. We have two fluids, basically water and air, and we have the obstacle. But in the case of huge density ratio between the liquid and the vapor phase, we may think to neglect the lighter phase. And this is the reason why we couple the lattice Boltzmann approach with a free surface one. As I already told you, that work has been supported by the Italian Ministry of Education in the project named Combined Numerical and Experimental Methodology for Fluid Structure Interaction in the Free Surface Flows under Impulsive Loading. More specifically, why are we interested in dealing with fluid structure interactions with lattice Boltzmann simulations? Basically, this is everything is driven by LBM simplicity in implementation and its parallel declination. Then LBM can assure us high computational speeds with respect to traditional solvers, and moreover, LBM allows us taking into account multi-scales phenomena. Then we have decided to couple the LBM framework together with a free surface approach in order to have high accuracy in a relatively short time. I mean, it's always dependent on the grid sites you are interested in and on the domain you're interested in. I will be really fast because I think that most of you know better than me that slide. I will just to point out that with the lattice-Boltzmann equation and with the lattice-Boltzmann method, we are looking at the mesoscopic approach rather than being macroscopic or microscopic. The lattice-Boltzmann in its general formulation with the Bandagar-Gross-Krock collision operator approximation is the one reported in equation 2. But as I already told you, we are going to implement the KBC model rather than the BGK1. So we have to decompose the distribution function f in 3 different moments, and in a while I will tell you who are these moments. And basically the KBC aims at minimizing the H function, the entropy, in the post-collision state. By this way, we have to define a new mirror state in order to recover the collision operator. Obviously, in a special case, we are able to retrieve, to obtain the standard lattice Bandagar-Gross-Krock collision operator. So the LBGK is a subcase of the KBC approach. But the important feature of the KBC, which is really appealing for us, is that it allows us to deal with slightly turbulent flows and in transitional flows with using relatively small grids. So we do not need a really huge computational grid in order to work with transitional and turbulent flows. I will be really fast on the theoretical aspect because I will stress a little bit more on the test case we are using, but some theory is needed for who of you is already aware about the BGK collision operator. You see that the viscosity is the viscosity definition with respect to relaxation time is slightly different with respect to the BGK standard definition, and we have defined a mirror state as a function of the equilibrium distribution function and the distribution function f itself. By defining the viscosity by means of the parameter beta, we are able to retrieve the Navier-Stokes solution. As I told you, the KBC starts from the decomposition of the population F into 3 moments. The moment key, which represents the kinematic part, the S representative of the shear part, and finally the moment H representative of the higher order moments. Every iteration, we are accounting all these 3 moments, and we are minimizing the entropy function in order to evaluate the parameter gamma. In the case of gamma equal 2, the KBC represents exactly the BGK model. In the case of multiphase flows, where we have a heavy fluid in contact with a light fluid, we may think to neglect the light fluid, in that case the gas, the air, in our test cases, and we are going to solve only the fluid domain. The fluid domain and the interface one. The interface is the narrow area which separates the fluid node from the gas ones. In order to do that, we define a mass fraction, epsilon, which is the ratio in between m, the local mass, and rho, and that parameter epsilon may vary in the range in between from 0 to 1. Is 0 for the gas cells, which won't be solved at all during our computations, and this is equal to 1 for fluid cells. At the interface, it may vary in between 0 and 1. This is a schematic representation of the computational overhead introduced by the free surface model. You see that we have to take a particular attention to the interface because we are artificially tracking the interactions in between the gas and the fluid, and we are assuming that the gas pressure is acting on the fluid part and vice versa. it is important to point out that the fluid cell cannot be in direct contact with the gas one. They have to be separated by means of at least one interface cell. Okay, let's move towards the core of the presentation. So the moving boundary condition and the force evaluation. The moving boundary condition has been treated via the Grad's approach, which allows us to reconstruct the unknown populations by means of the pressure tensor and the flux J, and it is really accurate for moving and deforming boundaries. It has been demonstrated its accuracy for moving and deforming boundaries, so we have decided to use such an approach while considering our moving obstacles, while we have also to consider a refilling strategy, because whenever we have a moving obstacle into our domain, it will uncover some nodes which were part of the solid obstacle into the previous iteration. So we have to think how to refill, how to populate these uncovered nodes. Specifically in that approach, if you think that the dashed light blue line is the position of the obstacle at t-1, while the continuous blue line is the position of the obstacle at time t, we have uncovered the gray square. And in order to populate that node, we consider the velocity equal to the one of the wall. So we are imposing the velocity at the gray nodes equal to the ones of the node of the walls, and the density is taken equal to the one of the first fluid neighbor. By means of the macroscopic density and the velocities, we are able to reconstruct the equilibrium distribution function, and then we are imposing that the population F is equal to its equilibrium distribution function. Finally, at least for the first belt of nodes which are in contact both with the fluid and with the obstacle, we have to track the tensor, the pressure tensor T, and we have to evaluate the force exchanged at boundary via integrated its two components along the wetted surface. So in order to validate the model, we have considered a test case presented in an experimental work by Miao. It was its PhD thesis in 1988, and it was dealing with the impact of a rigid sphere in a calm water domain. The physical parameters are reported into the table. You see that the width of the tank is definitely larger than the diameter, is order of magnitude larger than the diameter, and the experimental Reynolds and through the numbers are reported into the second table. I have to admit that in our simulations, we have not considered such a high values of Reynolds, because in literature is also possible to find that the Reynolds is slightly influenced such a phenomenon. So for a matter of stability, we have decided to reduce the effective Reynolds number by a factor of 5. So we are dealing with a Reynolds number which is in the range of 15,000 up to 20,000, something like that, rather than being 95,000. But as I told you, there are some literature references which show that the Reynolds number is not affecting that results, and I've also confirmed in a publication we have published recently that the Reynolds is not affecting significantly such a phenomenon. The dimensional numbers we are considering are Reynolds and through the numbers, and for the comparison with experimental data, we have introduced the slumping coefficient. The slumping coefficient is the ratio in between the vertical component of the force exchanged in between the fluid and the obstacle and the inertia, basically. So it's a function of the inlet velocity and of the diameter of the obstacle. it is worth noting that we are considering constant velocity impacts. So this is not a free-falling, this is a driven impact. We have considered also the non-dimensional form of the time, and we have compared the results at different through the numbers. You see that the black dotted lines are the experimental findings, while the red continuous one is the results we obtained with our KBC free surface model. You see that the agreement in between experimental and numerical results is pretty good, both in terms of times and slamming coefficient trend. So we may consider that our code is well simulating such a phenomenon. This is the reason why we have decided to move a little bit and to characterize a little bit more the phenomenon, and we have decided to modify the aspect ratio of the obstacle. So we have considered the variation of the ratio Rx, Ry over Rx, where Ry and Rx are the main radii, the main radii along the two axes.
5 minutes left, Daniele, sorry.
Okay, perfect, thank you. Okay, results are pretty obvious. The thicker the obstacle with respect to the impact direction, the larger will be the slamming coefficient at 0 time. And we may see how the thicker obstacles with the ratio greater than 1 are aligned, the ratio less than 1 are characterized by the black, red, and purple curves are aligned towards the same values, while the thinner obstacles are assuming a slightly different behavior. Finally, I will focus on the problem we are actually facing up with, and this is the sloshing simulation and the comparison with some experimental data already published in the paper by Cavallari and others in 2017. We are considering a physical domain like the one represented in the figure, and you see that we have a tank of about 40 centimeters filled by 4 centimeters of water, and we can, for such a system, highlight a natural frequency Fw, which is a function of the length and of the height. We have introduced a beta parameter, which is the oscillation frequency of the tank with respect to the natural frequency, and we are comparing the results with the set of experimental data. We have started with simulating beta equal 0.7. So the amplitude of our sinusoidal oscillation is 0.7, the natural frequency Fw, and the amplitude of oscillation is 15 millimeters. You see on the top the experimental acceleration graph we have used as a forcing in our computational domain. So we have fixed the tank, and we have applied the horizontal acceleration over the wall fluid domain. We have evaluated the forces exchanged at the lateral boundary on the left and on the right, and you see that the agreement with the experimental data is pretty satisfactory, both in terms of frequency response, but also in terms of amplitude. After that, we have decided to move towards a more complicated test case. So we have decided to move towards the natural frequency of our system. The things start to be quite promising, but unfortunately, the simulation crashes. There is no way to get a stable simulation. Honestly, we are still trying to understand why, if we move towards the natural frequency, we have such a kind of problems. But also, with increasing a lot the grid resolution, we still have some instabilities as we increase the beta parameter. Any suggestion or idea is obviously more than welcome. So I will rapidly go to the end. we have in that work we have demonstrated the effectiveness of the KBC coupled free surface model, and the results are pretty encouraging, despite we are facing up with some difficulties in the case of sloshing while approaching the natural frequency of the system. Thanks for your attention. I'm definitely willing to answer to your question. Thank you.
So thank you very much, Daniele. Any question from the audience? No questions? So maybe just one quick from me.
Yeah.
How much expensive is the method overall, let's say, comparing to standard BGK?
I mean, the KBC.
Yeah.
Okay. I see what you mean. The KBC itself is, I think, 20% or 30% lower than the standard BGK, something more or less like that. Obviously, the free surface is definitely more expensive, especially if you move towards a parallel computation, because you have to perform the message passing information in between the processes more than standard BGK approach. Honestly, I didn't evaluate it so far the differences in terms of mega loops or computational speed, but I mean, just to give you a flavor on that, you are adding at least 3 message passing every iteration, due to the fact that the free surface is not local. You are modifying also the macroscopic quantities of your neighbors. So every time you do that, you have to perform again the message passing. So I think we are introducing a factor of 2 in terms of penalizations.
Yeah.
Something like that, I mean.
Okay, thank you. Ilya.
May I ask a question?
Yeah,
Hi,
sure.
Hi, guys. So, just about the last thing about the instability. So, what exactly the parameter this beta guy is the value?
Yeah, the beta, let me go back to the slide, is the ratio in between the oscillation frequency and the natural frequency of the system. The natural frequency of the system may be defined starting from the length and the h, which are the length and of the h of the water domain.
Yeah, but just roughly, what is the value of this? How close is it to 1?
For the first simulation, that one beta was equal to 0.7.
Oh, that's quite far away. No, for the last, for the unstable one.
0.9.
Oh, no, that should not be a problem. I mean, for the pure KBC, that's never a problem. That's...
Yeah, I think, but I'm not really sure about that. I think the problem is related to the left and right boundaries, where the free surface is impacting. You may have some adhesion, and you can locally have spurious currents which are causing some instabilities and then simulation rupture.
Yeah, so it somehow can be to do with the coupling at this point.
Yeah,
because,
but
I mean, I'm a bit surprised because 0.9 is not really very...
Yeah, and just to add another point of discussion, I also tried with the standard BGK coupled with a Smagoriski subgrid model with a relatively fine mesh, and the simulation was stable as well. So probably the treatment of the free surface at the boundaries is injecting some instabilities to the system. Probably, I don't know. I mean, it's...
That means, unfortunately, I cannot give you an advice straight away because it has to do with the coupling at this point.
Yeah,
I'm pretty much sure.
Yeah, because I mean, I can also tell you that I use the KBC for a bunch of applications without any kind of a problem of stabilities. I mean, I think. So I think this is definitely driven by the
no, I was just asking because we somehow are responsible for this part of that thing and not for the coupling so well. where to look at. I mean, 4.9 is absolutely typical.
Yeah. In fact, I was pretty surprised when I didn't find a stable simulation. I mean, I'm trying with a really fine grid size, about 2,000 nodes for 4 centimeters. So we are talking about 240 million of computational nodes for a 2D simulation. So it's pretty defined. So I mean, the strange thing is that it seems not depending from the grid resolution.
Yeah, so something else. Okay, sorry, I
Thanks.
So thank you again very much, and we can move to next speaker. But Sebastian May, I didn't see him actually.
Me either.
Is there Sebastian? Because I'm afraid he didn't show up. And no. So I guess in this case we wait maybe another minutes, but I don't think he will at this point present. I think we can just meet again in 40 minutes because I don't think honestly we'll present. We are already at 4 and 7, so let's meet in 40 minutes after the coffee break. Thank you very much. In free surface flow. So you can start 15 minutes of presentation plus 5 to answer the questions, and I will tell you when we are at 15 minutes. So the floor is yours.
Are you able to see my presentation now?
Yes, but if you put it on full screen, maybe.
Is it not in full screen now?
I mean, just in the like when you have to switch in presenting mode in PowerPoint.
Okay, I am, because I see the full screen, so I was thinking like this.
No.
Giovanni, sorry, we faced up with a similar issue that morning, and probably it is better if Antonio would not go into presenter mode, but it will use PowerPoint in designer mode, let me say like that.
Okay. If it's okay for the other, if everybody can see the presentation, is okay.
Okay, just 1 moment, because it seems like I cannot change the slides. Just 1 moment.
Yeah.
I will. Can you see the?
Yeah.
Okay. Let's start. Okay, this work basically goes within the framework of a multidisciplinary, multi-interest, given the group of people. Let me thank you, apart from the universities you see here. Let me thank also the University of Perugia, who provided us with the experimental lab. And as I was saying, the multi-interest group was crucial, as the starting interest for this work. As you can read, the aim is to assess the validity of a discrete numerical method to evaluate the hydrodynamic thrust in free surface flows. And the classical problem we studied is a standard for also for numerical studies, which is the dam break problem. As I was saying, the macro field within we moved was the risk management. Risk management related to water. That's to say, the possible damages and the possible risks that might occur after a dam break event. As I was saying, the dam break not only represents a standard to study in terms of practical and experimental analysis, but also it represents a standard for numerical studies. Still has a major theoretical and engineering impact. Basically, for what I said about the possible.
Sorry, Antonio. My apologies if I interrupt you. Are we at the first slide? Because I guess maybe the screen freeze.
Oh, sorry.
We just see the okay. Now we can Thank you.
Now
it's okay.
Okay. You see the two pictures of the dam break?
Yes.
Okay. As I was saying, on one hand, the dam break might lead to disastrous consequences. So the engineering research is crucial to prevent such events. On the other way, it represents a standards for analytical and mathematical implications. In this case, we performed an experimental setup, a set of experiments with a prismatic tank, whose picture is right here, equipped with 10 dynamic pressure probes.
Well, the slide didn't change yet.
What?
I guess we have issues with the slide because we still see the slide 6.
Oh, I'm sorry, I don't know how to.
Yeah.
It's always delayed because I change once I don't know if I did something wrong in sharing the screen.
Because I mean, but you are in the presentation mode. No.
I am in a presentation mode.
Okay.
It's currently saying you are presenting. So
okay, so this is some technical issue. I guess we cannot solve right now. So
I'm sorry.
Antonio, sorry, are you sharing the whole screen or only one application?
I'm trying the whole screen.
Okay. Just a try, a stupid try. Let's try to share only PowerPoint.
Okay, let's try.
I don't know if it works, but it is something easy to be managed.
How about now?
Yeah.
okay.
Experimental setup.
Do you see the picture?
No. So maybe don't put presentation mode. Exactly. Don't use the presentation mode. Maybe. And you scroll the document.
Is not in presentation mode because you can see the design bar for PowerPoint.
No, but he said that he was, because probably we cannot see the presentation mode. So if it if he doesn't put in presentation mode, maybe, yeah,
Okay.
like this. Exactly.
Oh, so I won't show the presentation mode in my PowerPoint, and I will scroll the slides like this.
Yes,
okay?
yes, exactly. Thank you.
Okay, okay. So this is the experimental setup with the 10 probes, dynamic pressure probes. The height of the water was in a cubic shape, so 220 millimeters in length and height, and the width was 200 millimeters. We basically compared, we tested, I might say, as a preliminary work, we tested the SPH method, which I will introduce briefly, with respect to experimental results for a dam break problem, and a standard classical computational approach, which was throughout the OpenFOAM interfoam solver, plus a Rance turbulence treatment. And of course, the interfoam implies the volume of fluid method. As for the SPH method, I will briefly introduce it, not to get too long. The SPH method is a particle method. It is also a meshless method, as for the, that's why the title of this presentation. And the particle transport are implemented through a Lagrangian approach. Sorry, I will. The basics of the SPH method are summarized basically in 2 steps. One step is the integral representation of a function. The very basic kernel function is the Dirac's delta function, or the other 2 kernel functions, which are the cubic spline interpolant, or a polynomial spline of 5th grade, which is the Wendland, which was actually the choice of our simulations. The core of the SPH method is the particle approximation. Basically, on a framework given by a radius of h length, we can collect a number of particles, which varies from time to time, and of course, from which it depends the validity of the simulation. And of course, this equality happens, or it's we could say it stands when the ratio between delta x, which is the distance between the interparticle distance, sorry, is closer to 0. So it's very, very small. So apart from the smoothing concept, which is basically the core of the method, the equations, the governing equations, are the usual governing equations. One of the other characteristic, which was fundamental in actually to assess the differences in our testing, is that the SPH method implies always that the fluid is weakly compressible. Even though we dealt with water, we actually implied this weakly compressibility. And this is done by basically by following a certain procedure. Being a Lagrangian method, each particle has a mass which is constant during time. So in order to solve this system, and you see here the divergence of velocity, the discrete divergence of velocity. In order to solve, we have to find the volume of each particle. And as a starting, as the initial condition, sorry, the HPH simulation impose a uniform particle distribution. So that means that the volumes are initially uniform. The density, which actually changes over time, is assigned as an initial condition, sorry. So that implies that throughout the domain, the physical domain, the fluid domain, the particles may have different masses. As I was saying before, the masses do not change. Why? On the contrary, the density field evolves. And this means that volumes may evolve with respect to density, following this ratio here. So, this is just to sum up the governing equations again. I want to focus just for one moment about the speed of sound. As you can see here, the implied equation of state is the Tate equation. And why? Why focusing on the speed of sound? Because it's strictly connected to the weakly compressibility hypothesis. Through the barotropic condition, the pressure field is derived directly from the density field. But the speed of sound is crucial to determine the time step length. Sorry. Okay. Yes, this is pretty much says what I already said, that the pressure comes directly from the equation of state and the density, and the condition is set upon the speed of sound in this way. So the time step is approximately a ratio between the smoothing length, h, that's to say the maximum radius of the smoothing support, of the kernel support, and C0 is taken as 10 times, at least 10 times, the maximum value between Umax or this ratio here. And basically, this condition guarantees that the density stays below 100% during the time evolution of the simulation. This is basically what guarantees us the weakly compressibility assumption. So, pros and cons of this method is explicit, and this is good to use on GPUs, sorry, rather than CPUs. There's an implicit fulfillment of the free surface boundary condition. That is why we used it for free surface study. The dumb break problem is one of them. On the other hand, and we will see this shortly, the weakly compressible fluid produces acoustic noise and spurious spikes, pretty much always in terms of pressure and density. Okay, now I will. I could go back to this slide just in one moment. I want to just to clarify. I want to let you see the testing metrics we actually performed. As I was saying, on one hand, we tested experimentally the dumb break, and with the exact same conditions, of course, we tested these 8 cases, bearing these 3 main characteristics of the SPH method. Of course, there are many other conditions we could have varied, but basically this was a preliminary test in order to assess one thing which is present, of course, in literature, but not so much for practical motivations, practical aims, which is the thrust, the hydrodynamic thrust assessment. So these three characteristics, I will go back and let you see very briefly, are the viscosity and turbulence treatment, which is basically divided into two possibilities: the laminar viscosity plus a subparticle scale turbulence, the classical Smagorinsky eddy viscosity, plus the stress the stress tensor with a Favre average. And the second is the artificial viscosity tested for the first time by we could call it the father of the SPH method, which is pretty much an empirical method, given that the alpha factor changes depending on the case under study. Then there's the density modeling. As you will see again on the testing metrics, we performed or a Molteni density diffusion term, which is a term in the continuity equation, or none. So the difference was between non-diffusion density diffusion term or the Molteni model. And the third combination, this is again on the Molteni density diffusion. It's a specification of how it's modeled.
5 minutes left, Antonio.
Okay, gosh, I will run. And the third combination is the time integration schemes, or a classical predictor corrector type, or the so-called Verlet scheme, which is we could say a pseudo predictor corrector, because we only have an actual step of predictor step, but non-corrector, if not for a correction every ns time step. So this is what we tested. I will run, but this is a very briefly picture of the experimental. The camera was not so fast, but this is the classical volume of fluid plus runs simulation. The mesh was not so fine, but it gives the idea of the dynamics. One thing which is important is that literature shows us that this SPH method is pretty good in kinematics, in modeling and simulating kinematics, but has still has problems in assessing, as I was saying, pressure and density. This is the result. I'm sorry for the pictures, might not be really clear. Here are the 10 different probes, as right here represented again. Here are the pressure, dynamic pressure taken for each of these probes. The highest is the first one. Is the shortest one, the one close to the bottom. And the two things I want to highlight. Oh, sorry. This is the I missed the experimental. This is the experimental result. The two things I wanted to show is the maximum value here. Here it's pressure in bars, the maximum value, and the fact that of course there was a delay in the actual how to say the rising of the baffle. So as you can see, the simulations have 1 second of time, and here it might seem a lot more, but it's actually as I represented, it's time over 100. So it's 100th of a second. So as I was saying, that the actual start of the dam break event is around here. So I let you see the VOF. I wanted to highlight just two things. Being a finite volume method, it is very smooth. it's not represented the actual spike, the blunt spike, as in the experimental case. And now we go to the SPH method for the case. I will show you just the first one, just to give you an idea. They are all very similar, kinematically speaking. This is we are seeing the particles here. So as you can see, it might well represent realistically what happens. But then we'll go into the pressure representation. So this is pretty much, you see the vortex here, which is very close to what actually happens, and very close to the continuum representation with the Navier-Stokes equations. And now we go to the pressure, and here you start seeing the main features that we wanted to overcome. First thing, many spikes, differently from the experimental and the continuum. But the maximum value is very close to the actual one. The first spike is underestimated here. It's clearly a numerical thing. Same thing happens for the second case. I'll skip some slides in order to be compliant to the time. And from the fourth case, I will explain why I jumped to the fourth. In the fourth case, we have a slightly overestimation of pressures, maximum pressures, but no more underestimation of numerical spikes, negative numerical spikes. Same thing happens basically for the case 5. Of course, the higher probes do not peak.
Antonio, sorry, can you go to the conclusion, please? We are running.
Yes, okay. I wanted just to let you see the third case and sixth case. As you can see here, not only pressure is absolutely a mess here at the sixth as well, but also the kinematics. I will go. As you can see, it's totally numerically gone, we could say. So the conclusions. Case 3 and case 6 have no filters, both in density and in viscosity. This is totally unbearable, we could say, for the method, for the numerical representation, and that's the reason why you've seen such an unrealistic pressure distribution. The conclusions. The spurious spikes are strongly dependent on the presence of density filters. A lighter dependence, I called it lighter, is on the integration scheme. As for the spurious spikes that you've seen. And that's why artificial viscosity affects the energy conservation and produces pressure instability. Why density filters are most strictly connected to spurious spikes. So SPH method, given further analysis, of course, might be a valid way to evaluate hydraulic thrust over surfaces. Many issues are still to be overcome, and it is crucial to find the best density modulation in order to solve the pressure field in a better way. Basically, let me say, this is I wanted just to show that the future work is wide open, and I just wanted to say that in conclusion, that SPH method are given the potentials of GPUs right now, are a good might be a very good way to overcome experimental issues with also in the assessment of hydraulic thrust. But there's the big problem of density discontinuities. There are still not well catched by the pressure, we could say. So this is it. I'm sorry I went long.
No problem. Thank you very much. Thank you for your presentation. Very quick question from the audience.
If I may, it's a very interesting talk. I've always been interested in the SPH method, but I have never really looked at it very carefully. It seems like a very good study of the various ingredients needed to make it work. Just a very basic problem which I didn't quite understand. So if you initialize it, do you have particles only where you have the fluid, or do you have particles everywhere and generate the full fluid for everything?
Yeah, I didn't specify it. You have particles in the whole field. So you have particles for air, for every phase. And there's also one thing I didn't specify, that also the boundary conditions are modeled by particles, given, there are basically three methods. A ghost system of particles. There are always static, no motion. And the dynamic way of solving boundary conditions, even for solids, and you actually solve the boundary conditions as if they were inside the whole system of equations, but with no motion and with a different energy. It's solved with different force in energy, static, and that's how you represent. So to answer to your question more directly, everything is particled, we could say.
Great, thank you.
You're welcome.
So thank you very much again, and thank you. And let's move to the other speaker, which is Norian Yuma. Norian, are you there? I don't see him. I guess he's not online. So let's wait a couple of minutes.
I saw him online on the other room.
I saw him as well, but he's now online in the other room?
I think so.
Okay, so maybe took the wrong. Okay, so maybe I will switch to the other room to tell you.
Antonio, sorry, you should stop your presentation mode in Google Meet.
Okay, yes, so she's coming into this room, so I apologize. Let's wait a couple of minutes. She should be online. Thank you, Professor Deller, for...
Not at all. It seemed worth a try.
Yeah. Here we go. Hi, Norian. No.
No.
Norian, we can. I see you are online, but okay. Now you're.
Hi.
Yeah. Okay.
Is that the other room? My presentation is now for Nurjan Jumaa.
It's in this room, so you should present here and now.
Okay.
Thank you.
Just will try to join to present. Yeah. Okay.
So you have to go to present now, which is on the bottom of the bar on Meet, on Google Meet.
Yes. So just present now and then share.
Yeah.
Your enter screen share.
Okay.
Then.
Yep.
I will choose from. Is that right?
Yeah, that's great. So now you can open your.
Okay.
Yeah.
I will go to the presentations.
Okay.
Is that fine?
Yeah, perfect. So you can also push hide at the bottom on the bar. So you see on the bottom of the slide that you have a bar. Meet Google.com is sharing your screen. You can put hide if you like.
Sorry.
No, okay. Yeah.
I like this. Okay. Is the
okay.
that fine now?
Yeah. Never mind. It's okay. You can go on presenting mode as before.
Can I start now?
Yeah. It's fine.
Yeah. Okay. Thank you very much. Sorry for bothering anyone. I was in the other room and I'm asking about the time because we are in UK and I think it's different times, 1 hour before us. Today I'm talking about breaking dam simulations with the multiphase lattice Boltzmann approach. And I'm from Plymouth University. We will give a small introduction for the general lattice Boltzmann method, then how we modify this classical lattice Boltzmann to the multi-phase model with high density ratio by using 3 distribution functions for the phase field model and pressureless Navier-Stokes, then solve this pressureless, make correct the velocity by solving the Poisson equation, and this approach is based on Benari 2014. We modified that one, which is used with single relaxation time. We modified that one to use expanding by the multi-relaxation to work with high density ratios for dam break and for high Reynolds number. So we will take different cases, 2 cases with the wet bed and 1 case with the with the dry bed and 1 case with the wet bed for this dam break. We will start with lattice Boltzmann. We have the equation, the lattice Boltzmann here, which is have distribution function, F distribution functions, and with the equilibrium distribution here. And this equation is recovered Navier-Stokes, which is important for dynamic fluid dynamics. Here, we use the 2-dimensional 9 velocities. As we see how this particles is moving, if we have these 9 distribution functions according to the 9 velocities, propagate this particle to the neighbor by using the streaming step, which is here. This is include the left hand side is represent the streaming step, and the right hand side is the for the collision step, updating the distribution functions here. And this one is for this equation is for the single relaxation time, which is the tau here. The relaxation time is just 1. Then when we come to the multi-phase model, here the first we will start with the Hilliard equation, which is the free energy represent with the first term, which is the gradient of the order parameter phi and the bulk free energy. And this equation have the two parameters k and beta, which is can specified by the width of the interface and the surface tension coefficients. And we have this order parameters from this equation. This equation for the Hilliard is recovered by first lattice Boltzmann equation, which is here F distribution functions. And this F distribution functions with equilibrium, their equilibrium distribution was F, and their weights W and H. And this should be satisfy the 0 first and second order moment for phase field model, which is here. And this, when we know the order parameters from the phi, so we can specify the density according to this equation by using linear interpolations. From the same technique is used to know the kinematic viscosity. So from the kinematic viscosity and the density, we can specify the dynamic viscosity, or we can know the dynamic viscosity according to the linear and find the dynamic according to depend on the density. So pressureless Navier-Stokes equation is the second part we use the second distribution functions to recover the Navier-Stokes, but here is pressureless because we depend on the classic lattice Boltzmann. So we need to solve this equation to correct this equation to correct the velocity, to find the right velocity by using the third part, as we said, with solving Poisson equation. This one is the equation of the lattice Boltzmann for pressureless Navier-Stokes equation, and the other one is with equilibrium distribution function, and also we have to satisfy these conditions here for 0 first and second order moment, with absence pressure, which is depend on the density. Here we can see this is the difference between the classical and the pressureless in the multiphase. Here it equals 0, and the other ones equal density, which some papers they use it 1 for simplicity of the density, but here for the multiphase for high density, here it is supposed to be 0. And to correct that pressureless velocity, we have the third part for density distribution functions named H, and N is for iterative process. Here we use several times to get the accurate result. And this one is here we correct this pressureless velocity with the star by adding the term of the pressure to correct and find the velocity to make the flow is compressible. Sorry, incompressible with the low Mach number. And this is the equilibrium distribution functions here, and they can compute the pressure with n iteration, and for the next time n plus 1, which from this part we can find the iterative process. In general, the algorithm of the multiphase model is start with define the variables and initialize the values. We have the three parts, important parts, as we said, the F and G and H. From F part of distribution function for lattice Boltzmann, we can know what is the order parameter, which is important to know what is the interface between two fluids, for example, or more than two fluids. But here we use two fluids, and the derivations from G part, which is the pressureless Navier-Stokes, we can find the pressureless here Navier-Stokes and the density with the viscosities. Then from to correct that one, we use the third part H and correct the velocities by iterative process, and we repeat that one several times until we get the time or stop when we get the convergence. And this one is in general for multiphase lattice Boltzmann for 2 dimensions. By using the multi-relaxation time here, we use the multi-relaxation to the pressureless Navier-Stokes part, which is G part, with 9 distribution functions, and these 9 distribution functions represent these values for density and energy and the flex with the other moments, which is 9 moment. And this one is G here. And this is, as we said, the equilibrium distribution function with the single relaxation time. We need to transfer that one to the M equilibrium by using these matrices and the inverse matrices, as we can see here. And this one, as we said, with the single relaxation time, this part is just 1 over tau. Here we have 9 distribution, 9 relaxation time, and not just one, according to this vector here. So that, according to our equilibrium distribution function in the single relaxation, we have this equilibrium distribution function with 9 values, which is a vector here. According to this one, we found this to the multi-relaxation time. For the numerical simulation, we start with Martin and Moyes data to set our code according to these dimensions and these values for height and width. And we use 2 cases, one with this with square domain, and the other one with the rectangular domain. We got a nice result with so we can see here with more resolution, increasing the number of grid numbers, we can get more comparable result with Martin and Moyes. And this one is experimental data. We compare our result here with the experimental data for 4 time, different time with the OKIA data here for 0 and 0.1 second, 0.2 and 0.3. And the second one is the second case is with the Colograssi. With the Colograssi data, when we compare the domain, it will be the height equal to half of the width. We also also get a nice result when we compare the result with our value here with fixing Mach number. With the wet bed, we have this setting for fluid flow. Here is compared with the rash data, and also we find nice result when we use multi-relaxation time, which is not supposed to get any result with a single. And here we have also compared with 4 different times scales: 0.2, 0.4, 0.8, 1.13 second. And our conclusion for this work is using multiphase with the high density ratios and modify from the single relaxation, which is dependent on Banari's paper 2014, to expand that work to the for the multi-relaxation time to get model with breaking down simulation with different cases here. And for future work, we wanted to extend that for 3 dimension, and that one required to parallel use parallel for 3 dimension, and we can extend that model for fluid structure interaction like the ship motion, which is need more than 2 fluid, I mean 3 fluids that time. We will model that with solid phase 2. Thank you for your attention.
Thank you very much for your presentation.
Thank you.
Thank you. Any questions from the audience?
If I may, I had a brief question here. So you introduced this multi-relaxation time method, but it seemed like the relaxation time values that you were using were similar to 1, right? So not significantly. And I've always felt that if you take relaxation times that aren't actually that different from 1, the multi-relaxation time doesn't help much. So do you notice much improvement using multi-relaxation time?
We use just for the pressureless velocity side, which have the viscosity, because it's important here and make the flows working. Before it's with the single, we try to simulate our code, because we simulate this code with high density ratios before for the Rayleigh and bubble and to pulsar flow, all these ones. But when we start to high Reynolds number, like breaking down, it's not working. So when we try to use the multi-relaxation, we use it for the G part here only, and we got nice results when we found this equilibrium distribution function here for our one.
Thank you.
Thank you.
Other questions? So if not, we can thank once again the speaker. Thank you very much. And thank you all for attending this session. And have a good evening, good morning, whatever it is, to everybody. meet tomorrow. Thank you very much.
Thank you very much. Thank you.
Bye.
Thank you.